Good evening, everyone. Welcome to live session 11 of NPTEL course on mechanics of material. So today we'll cover the topics which are included in week 11, and we'll solve on some problems which will help you to solve the assignments. Okay. So these are the sample questions I have written for you initially, but first we'll cover up the concepts covered in week 11. Okay, and then we'll move forward. Okay. So in week 11, we have seen two things. So first is about the pressure vessels. What is the hoop stress? What is the axial stress? What is radial stress? And then we studied about the failure criteria on the basis of hydrostatic sensitive materials and hydrostatic insensitive materials. And then we defined on different failure criteria such as Tresca condition, von Mises condition, Rankine condition, Mohr-Coulomb condition, and finally Draeger-Prager condition. Okay, so I won't go much into the detailed parts. I'll just give you the concept that what is the logic behind all these things, and then we'll solve one by one questions. Okay, so firstly I'll go with the pressure vessels. Okay, am I audible?
Yes, sir.
Okay, so previously also we are doing two types of cases, like in terms of walls also, when we see the sections, thick wall sections, thin wall sections. Here also in pressure vessels, two types of cases are there. First is thick wall, another is thin wall. Okay, so whenever in the exam point of view also, whenever you are solving the question, first check in the question what has been written. Okay, thick walled or thin walled, whether the section is thick walled or thin walled, whether the pipe is thick walled or thin walled, because the formula or flow of shear will change, so it will impact your answers also. Okay, so first I look into the thick walled pipes. Okay, thick walled pressure vessels. Thick walled pressure vessels. Okay, so in the lecture also, if you have seen the lectures, sir has given you the different cases. Like suppose I'll draw one example. Suppose an annular cylinder has been given to you. Okay, and the radius for this cylinder from the center, inner cylinder is Ri, and for outer cylinder is R0. Okay, and suppose we have applied the pressure from inside. This pressure is Pi. Okay, and outside also you are applying a pressure of P0 or PE, P external. Okay, so what I'll do, I'll give you the formula for a generic case, and then you can deduce that formula to specific cases also. Okay, so the generic formula is that when we have applied the outside pressure as well as the inside pressure also. Okay, so I'll derive this thing in a very brief manner. Okay, I won't go into much details. For details you can watch the lecture again, but for your better understanding I'll just give you some points. Okay, so suppose this is an annular cylinder in which inside pressure Pi is acting and outside pressure P0 is applied. Okay, now what are the other cases you can get? Suppose internal pressure is not given, so you can put Pi to 0 for the final formula. Or else, if suppose they have said you that external pressure is not present, then you can put P0 equal to 0. So I'll give you the general formula, and then as per the case given in the question, you can deduce. Okay, we'll see the example also. So suppose this is the case. Okay, generic case in which pressure is applied at the internal also and as well as the external also. Okay. So first, in all these things, we assume the displacement field. Okay, I'll go this part as quickly because already this has been covered in the lecture. Just I wanted to state the formula. That is what the real meaning of this case is. Okay. For all much details, you can see the lecture. So the displacement field. First, I'll write. See, in the week also, lectures also, sir has stated two types of approaches: stress-based approach and the displacement-based approach. Because what we follow always is like this diagram, which we are telling you from the first day onwards. It force directly doesn't relate to displacement, so we need two additional quantities. What are those? Strain and stress. Okay.
Yes.
So now, if we are using displacement field approach, so what we'll do? First, we'll go from displacement to strain. Okay. Then we find strain, and from strain we just relate it to stress, and from stress we relate to force. Okay. This is how we move in a displacement based approach. So now we assume displacement field. So here, what we assume is that our displacement is proportional to the radial measurement. Okay. So, and for other values we are not considering, like circumferential displacement as well as axial displacement. Suppose your pipe is like this. What does this mean? Suppose your pipe is like this, both ends fixed, so it cannot change its length, no, because both ends are fixed. So we are not assuming any axial displacement. Okay. 0 dot e theta plus 0 dot ez. So ez represents your axial displacement. Okay. Understood? What do you mean by axial displacement? This length. Okay. E theta represents your circumferential displacement. What do you mean by circumferential displacement? It means that the shape of your pipe, which is circular now, will not change it to some other shape like ellipse. Okay. So we are not assuming that also in our case. Okay. And UR is your radial displacement. What do you mean by radial displacement? Since we have applied a pressure inside in the circle, it will become something like this after some displacement. It will not change its shape, but it will somehow, some thickness will be changed. This two thickness. This will be also be displaced outside. Okay, whatever be the displacement, we don't know. Will okay. So this thickness will be changed with this. Okay, this initially T will become T1. So this is known as radial displacement. Okay, so hence we are assuming radial displacement and no circumferential displacement and no axial displacement. So hence our displacement field will be equal to UR, which will be a function of R. R means radius, from inside radius to outside radius. Inside radius is Ri, outside is R0. So this is our displacement field. Okay. So now once you got the displacement field, what we do to get the strain? Epsilon is nothing but half of grad of U plus grad of U transpose.
Yes, sir.
This you know. See, I won't write all the formulas like how to get these things. Okay, you can solve the formula directly. I'll just tell you how we are relating. Okay. So now once we get the strain, can we get the stress with the help of Hooke's law? Constitutive relation. So how the stress is given? Sigma is equal to lambda trace of epsilon into identity matrix plus 2 mu e. This is the formula.
Yes, sir.
Where lambda and mu are Lamech's constant. So first we defined our displacement field. Then we First we define our displacement field. Then we see the strain. Then finally we relate the strain to stress. Okay. Now from stress we need to find out the forces. So for forces, what we do? We use equilibrium equation. What is this? Divergence of sigma plus rho b is equal to rho a. Okay. So in our case, we assume body forces to be 0 and acceleration to be 0. We are assuming body to be static, okay, not dynamic, okay. So hence, divergence of sigma will become 0, okay. So this is the first step, this is the second step, this is the third step, and this is the fourth step. Okay, understood till now?
Yes.
So after doing this, so you will get a formula which will say this thing, lambda plus 2 mu d2ur by dr square plus d by dr of ur by r equal to 0. Okay, this formula you will get after putting divergence of sigma equal to 0. Okay, you can see the lecture also, similar formula you are getting it there also. Okay, I added nothing new. Okay, what I'll do new is after this thing. Okay, so we see that Lami's constant are non-zeros. Okay, this both additive term cannot be 0. Okay, so hence this is 0. Okay, so after solving, integrating this, the final result you will get is that ur is nothing but c1 r by 2 plus c2 by r. If you have seen the lecture, you will be familiar with this formula. Okay, what is ur? Displacement, radial displacement. Okay, so now c1 and c2 are constant. So how to find this constant? That is a question. So for this, the fifth point will come as apply boundary condition. Okay. So in the lecture notes, you will see that it is solved for the internal pressure and it is assumed that external pressure is 0. But today what I'll do, I'll just give you the generic formula in which external pressure is also applied. So if other case will come that external pressure is 0, you can directly put P naught equal to 0. So you will get the same formula. Got it? So the boundary condition for that will be equal to, one second. When pressure is applied internally as well as externally. So traction at inner surface is in the minus ER direction, given as PI ER, and traction at outer surface, which is equal to in positive ER direction, equal to minus P naught ER. Understood why I took minus P naught and why I took positive PI? See, PI is towards outward direction, which is positive. P naught is towards inside direction. Okay. Okay. So that's a negative. So these are the two boundary conditions required. What does this mean? That sigma RR at inside radius is equal to minus PI. This means minus sigma RR at R naught is P naught. So we'll change it to write as, we'll change and write like this. Sigma RR at R naught is equal to minus P naught. Okay. So these two are the boundary conditions you have to put. Okay. So once you put this boundary condition, you will get the constant values. C1. You can write in your notes also. This will be helpful for your exam also. You can do all the calculations and check whether the constants I am giving is correct or not. Although it's correct only, but for your better understanding, you can derive by your own also. Okay. So the two constant values will be equal to Pi Ri square minus P naught R naught square You understood now what is Pi, what is P naught, what is Ri, what is
Yes,
R
sir.
naught? Yeah.
Yes,
Okay. Upon lambda plus mu R naught square minus Ri square. Okay. This is a constant one, C1. And C2 you will get as Pi minus P naught Ri square R naught square upon 2 mu R naught minus Ri square. So this is a generic formula to find constant C1 and C2. So suppose in the lecture note, the external pressure is not given. So you can directly put P naught equal to 0 for no external pressure. Okay. You will get the same constants as given in the lecture notes also. You can cross check this thing. Okay.
yes, sir.
So suppose if in the question they will ask the internal pressure is not applied, only external pressure is applied. You can put Pi equal to 0. Okay, understood? Let put P not equal to 0 for no external pressure. Okay. So this is C1, C2. Now finally what's the motive of finding all these things is to find the stresses in the radial direction, in the circumferential direction, and in the axial direction. The circumferential direction stress is known as hoop stress. Okay, I'll write that also. Okay, so sigma r, this is known as radial stress as a function of radius is equal to lambda plus mu c1 minus 2 mu c2 by r square. So when you put the formula, r sigma rr will become as a function of r will become pi ri square upon r naught square minus ri square 1 minus r naught square upon small r square minus p naught r naught square upon r naught minus ri square 1 minus ri square upon small r square. This is sigma rr. Okay, generic formula. All this I am doing is for thick wall cylinder. Okay, thick wall pressure vessels. Okay, thin wall I'll give you separate formula. Okay. Then next is the hoop stress sigma theta theta as a function of radius. This is known as hoop stress. Slash circumferential stress. Okay. So in terms of constant it is written as lambda plus mu c1 plus 2 mu c2 upon r square. So when I put the constant value, it will become sigma theta theta r will be equal to pi ri square upon r naught minus ri square 1 plus r naught square upon small r square minus p naught r naught square by r naught square minus ri square 1 plus ri square by small r square. So this is sigma theta theta. Okay. Last is axial stress. Sigma zz as a function of r. So why I didn't write as a function of r? Because it doesn't depend upon radius. Okay, it directly is lambda c1. So when I put the formula, so axial stress does not depend upon radius. Okay, this can be the potential question also. Okay,
सर वो सेम है बस उसको क्या कहते हैं
plus minus difference. Yeah, but in final answer it can give some different values. Okay, so
Oh, yes, sir.
sigma zz will be equal to minus nu. Nu means Poisson's ratio. Okay, pi ri square minus p naught r naught square upon r naught square minus ra square. Okay, this is the sigma zz. See, you can see nowhere small atom is there, so it's not a function of radius. Okay, whatever in whichever the plane you are, or in whichever the radius you are, it doesn't matter. The exact cells will remain the same. Okay, so these are the three basic formulas, generic formulas. Okay, so based on these three formulas we'll solve one question. Okay, first.
सर एक्सियल स्टेज से पर शो कर देते.
Yeah, one second, I'll just move down this thing first, then okay, so this is the axial stress.
सर ये लेमडा है कि आर है? R C1.
No, this one you are saying. One second, this one. This is lambda. This is nu, Poisson's ratio.
तो सर इसमें ही लेमडा है कि सारे में अपने लेमडा लिखा, मैं उसको आर लिख दिया.
No. Otherwise, all are there small r only. I didn't use any lambda and mu terms because these are Lam's constant. I need to change it in.
सर ये सिग्मा थीटा थीटा आर इक्वल टू लेमडा प्लस म्यू है कि आर प्लस म्यू है?
Yeah, lambda plus mu.
ओके सर. सर एक्सियल स्ट्रेस.
Okay.
सर हो गया.
Okay. Now we'll move on to the question part. So as you can see the question states that a sewerage water carrying pipe of 2 meter internal diameter and thickness 0.2 meter is buried underground. For the material that the pipe is made up of, its Young's modulus is 20 GPa and Poisson's ratio is 0.15. The center of the pipe is at a depth of 10 meter. Assume that the length of the pipe does not change and that the soil pressure is uniformly distributed on the external surface of the cylinder corresponding to the soil pressure at the center of the pipe, and the hydrostatic pressure due to sewerage water at the inner surface can be ignored, and that the density of the soil is 15 kN per meter square. Taking the pipe to be thick walled and acceleration gravity z equal to 10 meter per second square, we have to calculate the hoop stresses. Okay. So this is a long problem. I'll explain in a short way. Okay. So a similar pipe which I have drawn earlier also. This is the similar type of pipe. I'll draw again. Okay, this is the pipe they have given to us in the question. So you can see the question, it is written thick walled. Okay.
Yes, sir.
So we have to use the formulas which we have derived here. Okay. Now in this you can see in the question they have said that inner surface pressure, hydrostatic pressure due to sewerage water at the inner surface can be ignored. What does this mean? PI is 0, internal pressure is 0. Okay. Understood with the question? Okay.
आप उधर जो लिखवाए थे C1 में P.
Yeah, same will put. I'll give the formula one by one. Okay. But you understand the question first. Okay. Because reading question is most important. So first hint we got is thick walled. So we'll use whatever the formula we had derived earlier. Okay. Next hint we got from the question that the hydrostatic pressure due to sewage water at the inner surface can be ignored, which means PE is equal to 0. Okay. Now coming about the external surface. The soil pressure is uniformly distributed on the external surface of the cylinder, corresponding to the soil pressure at the center of the point. So it means P external or P naught is equal to gamma S into H. Gamma S is density and it is uniformly applied to the length. So H given H is nothing but depth. Okay, this is depth. Okay, suppose the pipe is like this, buried under the soil. Okay, and above you have a soil. Okay, so uniformly pressure is applied along the length, and this length is given to us as 10 meter. Okay.
Okay, sir.
Okay, I am representing in horizontal way. Vertically also same thing is there. Okay, both side soil pressure will be there for the height. Okay, 10 meter. And what is the density?
Density 15 kilonewton.
Yes. So what is the pressure? Gamma into H. Okay.
Gamma into 15 into
So
150.
Yeah. So 15 into 10, which is equal to 150 kilonewton per meter square. This is the pressure. Okay. Understood? P naught.
Yes, sir.
So now if I represent P naught, it will be like this. So P naught is applied like this, similar to our case, and Pi is 0. Internal no pressure is there. Okay. Now we'll come up to the radius. What is the internal radius they have given? See, internal diameter. 2 meter internal diameter they have.
That is 1.
So Ri is equal to 1 meter. Okay. Outer diameter they didn't set, but they said thickness. So outer diameter is nothing but Ri plus T. This is Ri and this is T. So Ri plus T is R naught. So R naught, so which is equal to 1 meter plus T is 0.2 meter thickness. So 1.2 meter. Okay, understood R naught?
1 plus कितना सर दिया है? T 0.2.
0.2.
Yes.
Okay, 0.2 meter.
Where, sir?
Yeah.
0.2. Oh, okay, sir.
Understood?
That is 1.2 meter.
1 second, I forgot. I changed something. 1 second. How to write it down? Yeah. So Pi is 0, P naught we calculated, Ri we got it, and R naught we got it. Okay.
Yes, sir.
So now, first question asked is, what is the
Okay, stay.
hoop stress at R is equal to R naught? Okay. Okay. So what is the formula, generic formula for hoop stress? This is the formula.
Sigma theta theta Pi Ri square.
1 second, I'll write here.
Yes, sir.
So this is the general formula of hoop stress.
Yes, sir. Yes, sir.
So now here we'll just deduce this formula for our case. See,
Yes,
Pi is 0. So sigma theta theta R, what it will be? This first term goes to 0 because Pi is 0.
Sir.
See, Pi is 0 now.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay. So whatever the left, R naught minus Ri square 1 plus Ri square upon R square. Okay. Now where they asked? Sigma theta theta at R naught. They have asked. Okay. So we'll just put R naught in terms of R. So our formula will become 1 plus RA square upon R naught square. Understood? Or any doubt?
Sigma theta theta is equal to
We just put C. From here to here, you got it? How we come
Yes,
from
sir. Yes, sir.
Now, now they have so now they have asked what is the hoop stress at R equal to R naught. So we just put from R, we put R naught. So here R to R naught square. Okay, understood?
Yes, sir.
So now just we will put the formula values now. So hoop stress at R naught. P naught is given as 150. R naught is 1.2 meter square upon 1.2 meter square minus Ri is 1 square. 1 plus 1 square upon 1.2 square. Okay. So you will get the answer as minus 831.8181 kilonewton per meter square. This is also we can write as kPa, kilopascal. Okay. Same thing. Understood? Any doubt?
No, sir.
Okay. Now second question they will ask. What is the hoop stress at R equal to small r equal to Ri? Okay. So same thing. See this formula. Copy. This is the hoop stress after putting Pi equal to 0. And now they are saying just put R equal to Ri. So what you will get? Sigma theta theta at Ri. Minus P naught R naught square upon R naught square minus Ri square. 1 plus Ri square upon Ri square. Okay, this will cut down. It will be 1. So it will become minus 2 P naught R naught square upon R naught square minus Ri square. Okay, understood? Hoop stress at Ri. Okay, so now we'll put the value minus 2 into 150 into 1.2 square upon 1.2 square minus 1 square. The answer you will get is minus 981.8181 kilonewton per meter square. Okay. Till now, any doubt for the both parts? So this generic formula which I have given.
सर ये कट कैसे हो गया?
The RI are same, no? This and this are same. We are finding R equal to RI.
तो सर वो RI स्क्वायर अच्छा स्मॉल r स्क्वायर. ओके सर.
Okay.
सर तो ये 1 नहीं लेंगे इसमें का?
हाँ, so 1 is there na, this one. So 1 plus 1 is 2. So this 2 I have written here. Now, see, if you cut these two things, you will get 1.
Okay, sir.
1 plus 1 is, you will get 2. Okay. Understood?
Yes, sir.
Okay. So, see, once you remember this generic formula, you can solve any problem in pressure vessels. Okay. This is very simple. You just need to put what is there and what is not there. Okay. So, finally, third question. Third question is
RI square is equal to 12 internal radius.
where?
सर ये R naught स्क्वायर माइनस RI का स्क्वायर.
This is not 12, this is square, 1 square. One second, I'll write it differently. So as to 1 second. Okay, 1 square. Okay, here also.
सर इसको हम केपीए में भी सेम लिखेंगे ना?
Yeah, kilonewton per meter square is nothing but kPa. See, Pascal is nothing but Newton per meter square. Okay.
Okay, sir.
So K means kilo. Okay. So third part is, what is the axial stress? Okay. Sigma ZZ. So as I have told you, sigma ZZ is independent of R. So sigma ZZ at R equal to Ri will be equal to sigma ZZ at R equal to R naught. Okay, because it is independent of R. Okay, understood this point. So what is the formula for sigma ZZ?
Minus V.
This is the formula for sigma ZZ.
Yes, sir.
So now we'll put the pi is 0.
सर तो हमको सिग्मा जीजी में तो आर तो लेना ही नहीं है ना?
Where?
Does not depend upon R.
So they won't ask you at any R. They will just ask you what is the axial stress. Okay.
Okay.
So sigma ZZ, pi is 0. So it will become minus P naught R naught square upon R naught square minus Ri square. Okay. Poisson's ratio given is, see, this minus and this minus will become plus. Okay. Okay.
What, sir?
See, this minus, when multiplied by this minus, it will turn out to be positive. Okay.
Yes, sir. Yes.
So what is Poisson's ratio? 0.15. P naught is 150 into R naught 1.2 square. R naught minus, I know R naught square minus R square. Okay. So sigma ZZ you will get as 73.6363 kilonewton per meter square.
Sir.
Yeah. Any confusion?
Yes, sir. ऊपर का RI कहाँ चला है?
See, pi is 0, no?
That is all 0.
Okay.
Oh, sorry, sir.
So this formula will help you. Okay, this is a generic formula. Any case given to you, just put the values, get the answer. Okay. That's why I derived this formula for you. Okay. So as to understand all the internal steps and how the formula is coming out to be. Okay. And if you want more details, you can see the video lectures in the week 11. First and second lecture will give you this thing. Okay. So this is first part of the problem. Got it?
Yes, sir.
So as I told you in the very first 5 minutes, that we always solve things for two cases. First is thick wall, second is thin wall.
Thin wall.
So now we'll move into the thin wall section. Thin wall pressure walls. What if the question will be given as thin wall pressure vessels? Okay. So here I won't derive because the formula is very simple. Okay, and generic also. So professor has given the detailed explanation for these formulas. Okay. So I won't go into the detail. I'll just give you the formula for this. So for thin wall sections, the hoop stress, sigma hoop, I'll write like this. Okay, hoop stress will be equal to Pi minus Pe or P naught. Anything you can write. Okay, by T into Rm. What is Rm? Mean radius. Okay.
Yes, sir.
Sigma ZZ or sigma axial will be equal to Pi Rm upon 2T. Okay. Understood? And here in thin wall section, we assume that radial stress to be 0. Okay.
इसमें, sir?
In thin wall pressure walls.
Okay, sir.
Okay, these three things are there. Okay, so now we'll move into the question part. Okay, I'll just move it down this question. Okay, so this is the question. See, a thin-walled circular tube with average diameter or mean diameter are same. Okay,
Okay.
2 meter and wall thickness 0.2 meter is subjected to an internal pressure 100 kPa acting radially outwards. The ends of the tube are closed. Okay, so the point to be understand is that thin walled it is mentioned. Okay,
Okay, sir.
so we'll use these formulas whatever I have told you here. Okay,
Okay, sir.
so first question they have asked is what is the hoop stress. Okay, so sigma hoop is nothing but pi minus p or p naught whatever rm by t. Okay, in this question what is pi? 100
PI
kPa.
is equal to 100 kPa.
P 0, no external pressure is applied. Okay, rm is nothing but 1 meter
Okay, sir.
and t is 0.2 meter. 0.2 meter.
Oh, sorry, sir. Thickness is correct.
Diameter is 2 meters, so radius is 1 meter. Okay,
Yes, sir.
so just simple. This formula is very simple now. Sigma hoop will be equal to 100 minus 0. Rm is 1 divided by 0.2. It will not be equal to 500 kPa. Okay,
PI is equal to 100 minus 0. Okay, sir.
next is what is sigma axial? Pi Rm upon 2T. Formula is this. So Pi is 100, Rm is 1, 2 into 0.2. Okay, so it will be 250 kPa. Understood?
Yes, sir.
Okay. Now they have last asked you what is tau max. That is maximum shear stress. Okay. Long back you have seen this thing. Okay. So see, I have told you these three are the stresses we got for the thin wall pressure walls. So what will be the state of stress? How will you write the stress matrix? Stress matrix will be equal to sigma r 0 0 0 sigma theta theta 0 0 0 sigma z. Okay, this is 0 always. Okay,
Okay, sir.
so what will be the stress? Okay,
Okay, sir.
so now we have to just find first the state of stress or stress matrix. Sigma will be equal to 0 0 0 0 sigma theta theta 0 0 0 sigma z. Okay, or sigma axial. Okay, so it will be 0 0 0 0. What is sigma theta theta? 500 0 0 250.
Yes, sir. Sigma hoop is equal to sigma theta theta.
Yes,
Or sigma axial is equal to sigma jj.
yes, sigma theta theta is equal to hoop stress. Okay,
Okay, sir.
sigma zz is equal to sigma axial.
0 0 0 0 500 0 0.
Okay,
Okay, sir.
now one more thing. See, in the question it is written the ends of the tube are closed. Okay,
Closed.
So when the ends are closed and you apply a pressure, okay, so now ends will tend to move further. Understood? They will try to stretch, okay, but since they are closed, they can't stretch, okay.
Yes, sir.
So then they develop a compressive stress, not tensile, because the end closed thing will try to push them towards, okay, because they want to expand and we put it closed, so they want to put a reaction of opposite direction, compressive direction. Okay, this point is clear or not? Because of this, this 250 is minus 250 because it develops a compressive stress. Okay, see, suppose this is a fixed beam. Suppose I'll tell you. Okay, simple example I'm telling you, and suppose I'm hitting it. Okay, this beam tries to expand its length like this, but due to fixed end, can it stretch like this?
No, sir.
No. So the fixed end, what it will do? It will try to compress. It will exert a pressure, force onto the beam so that it can't move. Okay. So that is what this minus I signifies here. Okay.
Okay, sir.
This is important because it is asked in the question itself, said in the question itself. Okay. So that's what I'm always saying. Like reading question is very important. Thin walled means which formula you have to use. Internal pressure given, so internal PI is given to you. P naught is not given, so P naught is 0. Okay. These all things will be given in the question. So now last part. What is the maximum shear stress? So as you seen in the formula long back, what is tau max? It is nothing but half of maximum of absolute value of principal stresses. Okay.
Yes, sir.
So it is nothing but sigma 1 minus sigma 2, sigma 2 minus sigma 3, and sigma 3 minus sigma 1. Okay. See, since all the other things, this, and this, these all are 0. So this stress values are nothing but principal values only because only diagonal values are present. Okay. When matrix is a diagonal matrix of stress, it represents a principal stress. Okay. That's what you have learned in the previous lectures also. So now I'll write just half of max of what is sigma 1? 0.
0.
Sigma 2 is 500 mod 500 minus sigma 3 is minus 250. This is minus 250 minus 0. So what it will become? Half of max of 500 comma 750 comma 250. What is the maximum value? This one will be the
750.
so half of 750 is 375 kPa. So this is nothing but tau max. Okay. Understood? Or doubt?
सर ये -50 होगा ना?
This is modulus. Minus
550.
Okay.
750.
Okay. This value will take.
Okay, sir. Okay, sir.
So this is the second question. Understood what is the difference between the first question and the second question?
Yes, sir.
First question, they will clearly mention you that this is a thick wall. 375. 750 by 2 is 375. Okay. Here also what you have seen that any matrix in which only diagonal elements are present represents the principal matrix. Okay.
Okay, sir.
Because non-diagonal elements are 0. Suppose some value has been given here 10. So can you put sigma 1 like this? No. Then you have to find the eigen values. Okay. We'll see in the next example that is also. Okay. Understood?
Okay. Yes, sir.
So that's what I am telling you. Every topic has 2 parts from weeks 8. like thick walled section or thin walled section. If a channel section is thick walled, separate shear flow will be there, so separate formula is required. If a thin wall is given, shear flow is different. Okay, understood? So similarly to pressure vessels, thick wall, thin wall. So reading question is very important. Okay,
Okay, sir.
see here they will clearly mention thick wall or thin wall. If thick wall is there, this set of formulas you have to use this, this, and this. Okay. If thin wall is given to you, separate formula you have to use like this. Okay, understood?
Okay, sir.
And you have to read the question carefully. Okay. So now we move on to the third part. Okay, third part I first cover the basic topics. Okay, what has been covered in the week 11 lecture. This is based on the failure theory. Okay.
Okay, sir.
Okay. So in failure theory, what did you understand? Like, suppose someone has given you a stress state. Okay. So you cannot apply indefinite amount of stress or pressure. No, it has some material properties that it can yield up to some certain limit only. Okay. Suppose in rubber band, for example, in rubber band, you can take example. A rubber band has a capacity of 10 kilonewton of load you can apply. But if you apply 12 kilonewton load, will it withstand that load or it will fail on that load?
What, sir?
See, in a rubber band, if rubber band has a capacity of applying a 10 kilonewton load only, but
Yes,
you are
sir.
applying more than 10 kilonewton, so will it fail or not?
Fail, sir.
Yes. Similarly, for different materials, different failure theories are presented. Okay.
Yes, sir.
So all these failure theories are based on stress. Okay, not strain.
Okay.
Okay, the expression has been very much clearly given in the lecture. Why not strain? I'll just tell you the basic thing. You can go and see the details. Is that suppose, see, all these things we deal with stress and strain is mechanical. What the stress we are calculating is mechanical stress. Okay, but
Okay, sir.
whereas if you heat a cantilever beam, it will generate a strain, but it will not generate a stress. Why? Because heating a body, it will develop a thermal strain and not mechanical strain. Mechanical strain will be zero. So our mechanical stress will be zero. So that is one of the reasons that we use failure theories in terms of stresses. Okay. For more clarity, you can go to lecture and see. It is presented in lecture 5 of week 11, part 5. So the main idea is the failure theories are a function of stresses. Okay.
Okay,
So
sir.
this is the symbolic way of representing this thing. Okay. So now which type of stresses? So in failure theory, you will always deal with principal stresses. Sigma 1, sigma 2, sigma 3 and principal directions N1, N2 and N3. Okay. So this sigma 1, sigma 2 and sigma 3 are nothing but principal stresses. And N1, N2 and N3 will be principal direction. Till now understood?
Yes, sir.
Okay. So in your level right now, we'll deal with the isotropic material. Okay. So what do you mean by isotropic material? So it means that there is no preferred plane of failure. See, this N1, N2 and N3, they say that in which plane it is going to fail. Suppose it has three planes, three directions are there. So the material can fail in any direction. You don't know. But when the material is isotropic, you will say that it is not dependent on direction. Okay, it will fail in any other direction. No plane is preferred. The meaning is this. Okay, no failure plane is preferred. Okay, so which means that the failure theory will now only be the function of principal stresses. Okay, and these principal stresses are based on principal invariance. So we'll write a new function which represents K1, K2, K3. Okay, where K1 is nothing but principal invariance. What is K1? Trace of sigma. K2 is equal to my half of trace of sigma square minus trace of sigma square. Okay, and K3 is determinant of sigma. Okay, now this failure theory is subjected to two subdivisions. First is hydrostatic pressure sensitive. Here I like pressure insensitive, and here it is hydrostatic pressure sensitive. What does this mean? Insensitive and sensitive. Suppose a material has been dipped in a fluid and it fails. It means the material is hydrostatic pressure sensitive. And if you immerse a material in a fluid and it doesn't fail, so it is meaning is hydrostatic pressure insensitive. Okay.
Oh, sir, once again.
Yeah. Again, should I tell?
Yes, sir.
So hydrostatic pressure sensitive means if you immerse a material in a fluid and that material fails, it means sensitive to hydrostatic pressure. And suppose if you immerse a material in a fluid and it doesn't fail, it means it is hydrostatic pressure insensitive. Okay. So other name what we call for this material is ductile mode of failure.
Okay, sir.
What is ductile? It's just like steel. If you just stress, suppose you have a steel rod and you have a glass. If you just like put it down, like throw the glass, it will just brittle failure. It will just crack. Suddenly it will crack. But steel, it will not crack. It will just stretch. If you stretch the steel bar, it won't crack like glass in basic language. Understood? So delaying the brittleness of the failure is known as ductile mode of failure. Sudden failure is not there in ductile mode. Okay. So what is the steel? Steel, it will elongate. It won't crack suddenly. It will elongate to certain point and then at one point it will crack. Whereas in terms of glass, if you just throw the glass, it will crack suddenly. It will break suddenly. Okay. So that sudden breaking or sudden failure is known as brittle mode of failure. Okay.
Okay, sir.
And delaying of that sudden failure by exceeding its limit, okay, and by elongating the steel bar after exceeding the load is known as ductile mode of failure. Okay. So this type of failure is generally governed by Tresca criteria and von Mises criteria. Two types of failure theories are given for this type of failure. Okay. Not theory criteria. Okay. And for this brittle mode of failure, three theories are there. One is Rankine criteria. Second is Mohr-Coulomb failure. And last is Drucker-Prager. Drucker-Prager. Okay. For detail of each criteria, you can visit the lecture. Okay. Just for the overview I have given to you. Okay. Now we'll solve an example and see what does this mean. Okay, I'll just touch upon the Tresca and von Mises criteria because these two are the important ones. Okay, for your level right now.
कौन
Okay.
सा ये टेक्सटाइल एंड नॉन बेसिस
Yeah. Okay.
यस ओके सर
But I'll suggest you to go through each and every criteria. Okay, to know. Okay. And if you have doubt, you can ask me anything. Okay. So we'll go to the question now. So the question states that we have a state of stress, okay, in which sigma xx is nothing but 400 MPa, sigma yy is given as 300 MPa,
yes sir
and sigma xy is given as 300 MPa. Sorry, 100 MPa.
okay sir
Okay. So these are the stress values given to us. Okay. And they say that if the yield stress from the pure shear test on that material is sigma y, which is given as 175 or 200 MPa. Okay. So they said whether this plate or this material will fail by Tresca criteria or not, or it is failed by von Mises criteria or not. Understood?
yes
So you have a stress values, and they said that the material has the yield stress value of 200 MPa from a pure shear test. Okay. So whether the material will fail according to Tresca criteria or von Mises criteria or not. Okay. So first of all, for these questions, first you have to create the stress matrix. Okay. What is the stress matrix for this case? Sigma xx is 400, sigma xy is 100, sigma yy is 300, rest are 0. So what this state of stress is, this is known as plane state of stress. Understood?
yes sir
This is the stress matrix, okay? In which sigma xx is 400, sigma yy is 300, and sigma xy is 100, okay? Now first, so now what I said you here is the failure theories are governed by the principal stresses, okay? So this matrix is not principal matrix.
no sir
This is a generic matrix. So first step is to find out the values principal component of stresses, okay?
okay sir
So now we have two rules to find out. Okay. First is the Mohr circle equations, as we have seen long back, to find out the principal stresses values.
yes sir
And other is the invariant formula that we got. What is that?
yes sir
Sigma principal is k1 lambda square plus k minus k2 lambda cube. Sorry, k1 lambda cube plus k2 lambda square minus k1 lambda plus k3. Okay. So here we use Mohr circle equations. Okay.
yes sir
To find out principal stresses. So sigma 1 principal, okay, will be given by sigma xx plus sigma yy by 2 as per the Mohr circle equation plus under root of sigma xx minus sigma yy
power by 2 का whole square
plus sigma xy whole square. This is sigma 1. Sigma 2 is same formula but a negative sign in between. Okay. And and sigma 3 is 0 because these and these are 0. Okay. So what is sigma 1 if you put the value? Sigma xx is 400 plus 300 by 2 plus under root of 400 minus 300 by 2 whole square plus 100 whole square. Okay. This will be 400 plus 300 is 700. 700 by 2 is 350 plus under root of 400 minus 300 is 100. 100 by 2 is 50.
50.
So 50 square plus 100 square. Okay.
Yes,
So if you solve this thing, you will get sigma 1 as 461.8033 MPa. Okay. All these are in MPS. Okay. Sigma 2 400 plus 300 by 2 minus under root of 400 minus 300 by 2 whole square plus 100 square. So what you will get 350 minus 50 square plus 100 square. So answer you will get as 238 plus 8033 MPa. Okay. So now your principal stresses matrix will be look like 461.8033 0 0 0 238.8033 0 0 0 0. This is your principal stress matrix. Okay.
अच्छा सर, अब वहाँ 400 की जगह पे आप सिग्मा 1 रख दिए हैं.
Yes. So this is your principal stress matrix. Now you can use the failure criteria. Okay. To evaluate whether your material will fail or not. Okay. So now first is according to Tresca criteria. So for pure shear test, in the question they have said pure shear test. Okay. Tresca criteria is tau max should be less than equal to K. Okay. Where this K is a material property. Okay. And it is given to us in the question, which is nothing but 200 MPa. Okay. It is question, it is given to us. Okay. This if the yield stress from the pure shear test is this. Okay.
200 MPa.
Yeah. So this is given. K is given. So now we have to calculate tau max. So you know tau max is nothing but half of maximum of absolute value of sigma 1 minus sigma 2, sigma 2 minus sigma 3, sigma 3 minus sigma 1. Okay. So this is nothing but half of maximum of, sigma 1 is 461.8033 minus 238.8033 comma 238.8033 minus 0 comma 0 minus 461.8033. Till now clear? So tau max will be equal to half of maximum of, first will become 223, I guess. I have to check. 1 second. Yeah, 223. Absolute value second is 238.8033 and third one is 461.8033. So what is the maximum value? This
461.8066.
tau max will be equal to half of this value, which is equal to 230.901 MPa. Okay.
Yes, sir.
So now you can see from this 1 and 2. According to Cheska criteria, tau max should be less than equal to K as per the criteria for a material to be safe.
Yes,
but
sir.
here tau max is
Greater than.
K, which
Yes, sir.
means material
Not follow.
will fail.
तो no होगा ना?
Yes, material will fail.
Yes, sir.
If they will ask whether the material will fail or not, you will say yes. Okay, understood? So now second we'll move to von Mises criteria. So for pure shear, von Mises criteria will say K to D should be less than equal to K square. Okay. So K is given to us as 200 MPa. So K square will be equal to 200 square.
Yes, sir.
Which is equal to 4 lakh. Okay, sorry, 40,000. Okay. MPa square. Okay. Now what is K2D? K2D is nothing but 1 by 6 of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. This is the value of K2D.
अच्छा
Okay,
सर, ये
formula.
one by formula है, मतलब K2D.
Yes, yeah, this is the formula.
Okay, sir.
So now we know all sigma 1, sigma 2, sigma 3. We'll just use the formula. Okay. Sigma 1 is 461.8033. Sigma 2 is 238.8033 square plus sigma 2 is 238.8033. Sigma 3 is 0 plus 0 minus 461.8033 whole square. Okay. So if you calculate all these things, you will get the value as 53,336.38. Okay. So here also you can see K2D is greater than K square. See this and this value.
What, sir? Yeah,
This is
sir,
K2D.
greater than.
Okay. And this K square is this. So if you see these two values, you can see K2D is greater than K square. So which means material will fail as per von Mises criteria also. As per.
सर ये मतलब 1/6 से divide कर.
Yeah, after final answer. Yeah.
Okay, sir.
So understood? Now.
Yes, sir.
So for this type of questions, first you have to make sure step by step. First, form a stress matrix given to you as per this. Okay.
Okay, sir.
Now failure criteria only works on principal values. Okay, this is the main point. Okay. So just with this data matrix, find the principal values. Okay.
Okay, sir.
How will you find principal values? You have two options. Either to use Mohr circle equation or to use cubic equation derived from invariance, principal invariance. What is that equation? K1 lambda cube minus K2 lambda square plus K3 lambda. Lambda cube minus K1 lambda square plus K2 lambda minus K3 is equal to 0, where K1, K2, K3 are principal invariants. Understood?
Okay, sir. Yes.
Remember or not that formula? Or shall I write another way?
No, sir. I understand.
Formula is lambda cube minus k1 lambda square plus k2
Plus K2.
lambda minus k3 is equal to 0. k1, k2, k3 are principal invariants. Okay.
तो सर वो इनवेरिएंट वाला फार्मूला बता रहे हैं आप?
Yes. So either you can use this or Mohr circle equation. In this problem, I have used Mohr circle equations. Okay. So then you can find all the values and then form a principal stress matrix. Okay. This matrix.
Okay,
so after finding this matrix, you are eligible to use the failure theories. Okay.
Okay, sir.
Now in the question they will ask you as per which criteria this material will fail or not. So in this question I have used two criteria. First is Tresca criteria, second is von Mises criteria. And in the question they have said the material has a yield stress in the pure shear test as 200 MPa.
200 MPa.
So they have given us the value. So now as per Tresca criteria, tau max is less than equal to K and we know how to find the tau max. Okay.
Okay.
Similarly, for the von Mises criteria, we know K2D is less than equal to K square for the material to be safe. And K2D is calculated by this formula. But what we found? That K2D is greater than K square. Hence, the material will fail by von Mises criteria as well.
Yes.
So these are the three set of questions which will help you in doing week 11 assignment. So first we saw thick walled pressure walls. Second we saw thin walled pressure wall. And third we saw failure criteria. Okay. We first move on with the theory part, like how to solve this question, what are the generic formulas, and we see examples one by one. Okay. So if you have any other doubt in other theories, you can ping me up, or if you have now, you can ask me also. Okay. So these three questions will help you in doing the assignment. I hope you got all these things right. Okay. Any doubt?
No, sir.
Okay, then shall we exit?
Yes, sir.
Okay. Thank you for joining the class. See you next week.
Thank you, sir.